My name is Andreas. I'm working with Samsung in the global open source team. We're the guys with the funny little ghost, Linux Ghost. Thanks for having me. Before we get started, I just want to quickly gauge the room. How many people in here are writing code in their day jobs? Okay, like 5. So how many of you are familiar with the Rust language, like know of it? Okay, a little more. And how many of you have like written Rust programs for work or? Okay, 3, cool. Yeah, so I'm going to talk about block device drivers in Rust for the Linux kernel. And I'm going to talk about memory safety and why we need it, not just in the kernel, but in general, and why it's really important. And then I'm going to talk about what does memory safety mean from a Rust perspective. Then I'm just going to quickly go over the Rust for Linux community and where we are at and where we're going. And then at the end I have some code examples for how to use the block MQ abstractions to implement Linux block device drivers. So why should you care about memory safety in your code? These are some statistics I collected over the past year. The first 2 from Microsoft and the Chrome project are, I believe it's from Microsoft Edge. And they are C++ projects, and they say that 70% of all of the security bugs are memory safety issues. So these are stuff like stack overflows and null pointers that go, probably not null pointers, but pointers that go where they shouldn't. We also have a study of bugs submitted to the stable Linux trees for the driver directory, and they find that 20% of the bugs, not just security bugs, but bugs in general, submitted to the stable trees are memory safety issues. Another study finds that 65% of all Linux kernel vulnerabilities come from memory safety issues. And we have the Android open source project stating that memory safety vulnerabilities disproportionately represents the issues they find. And the last is a study that I did myself of all of the commit in the null block driver in the Linux kernel. And I find that 41% of all the fixes submitted to the null block driver are for memory safety issues. And so these issues are security issues that can lead to remote code execution or other security issues, privileges escalation and stuff like that. So they are really, we don't want them. They're really bad to have in our code. And the statistics show that even though like we're really careful, so these are prominent projects, we can't get around these issues. So our goal for the Linux kernel is to prevent these memory safety related bugs. And we think we can do that by using another language instead of C, a language that prevents us from making these bugs in the first place. And there's a few memory safe languages that you can choose, but probably the one that we should go with is the Rust language. So I believe, for instance, Python is also memory safe, but I don't believe anyone thinks we should put Python in the Linux kernel. So the Rust language is very similar to C in the sense that it's a language that's designed for systems programming. You have ahead of time compilation. The Rust compiler is built on top of LLVM. And we have low-level control. It works great for bare metal. We can use Rust on microcontrollers, for instance. And we have performance on par with the C++. And it's quite easy to interrupt with the existing code bases we have. And there's it's not it's a traditional language in the sense that all our control flow structures are familiar. Like we have if, for, while, loops, all of that stuff. Nothing super fancy. But it's also, in some sense, a vastly different language than C. So we have a very strong type system and then an elaborate type system that sort of has a more like a flavor like Haskell, if anyone is familiar with that. And we have a lot of features that you get from these more modern languages. Like instead of expanding include files to get like textually expanding include files, we have a proper module import system, so we don't need the compiler to expand the program text verbatim and then begin to parse it. And we have this, the most important feature we have is that we have a safe subset of Rust that is like provably absent of memory safety issues. You basically cannot make these bugs that you can make in C, for instance. And we achieve that by partially by static lifetime analysis, and then by the type system that we have. If you have any questions, please feel free to just raise them. So when I say memory safety, what do I mean by that, and what do I mean in the context of Rust? So when we say Rust is memory safe, what exactly do we mean? Well, we mean that we have three primary properties. We're memory safe, we're type safe, and we are thread safe. So the term memory safety covers absence of stuff like buffer overflows. When we write to a location, we know that the memory is valid and initialized and allocated. When we talk about type safety, we say that we are never going to confuse a type. So we are not going to take let's say a struct packet from the net layer and then misread the discriminant that says if this is like a TCP packet or UDP packet, and then interpret the data wrong. We can't do that. We check that statically. And lastly, we are thread safe, so we're not going to have any data races. We're not going to have multiple writers to the same location without synchronization. And that gives us absence of all of the bullets you have over here on the right side, which is very nice properties to have in a language that you are using to implement an operating system. So what is not covered by the safety guarantees? Well, the following bullets are not considered unsafe behavior. You're still allowed to deadlock. You're still allowed to leak memory. That is not unsafe behavior in Rust, and the compiler will not, by default, help you. Then you will need to resort to the same kind of tools that you will use for C. For instance, like we have the lock deblock, whatever it's called in the kernel. It's also not unsafe to forget to call your destructors. Integer overflows are not covered. We can have checks for them in the compiler. We can have the compiler insert checks for integer overflows, but having overflows is okay. And like logic errors, the last bullets, that's also not unsafe behavior. You can still very much code wrong and then have issues from that. So how are we gonna put this Rust in the kernel? And so if we put Rust in the kernel, are we then done? Just put some pieces of Rust and then no memory safety. Well, it turns out that it's not that, unfortunately, it's not that easy, because we don't want, and we can't, like rewrite the entire kernel in Rust. It's a huge project, and it's ultimately not what we're trying to do. And calling C code from Rust is unsafe. And what does that mean? That means that the Rust compiler cannot verify the invariants that it needs to verify when it calls into C code. It can't know if a reference that it passes, how it's going to be modified by the kernel code. So at this FFI boundary, we are going to have to verify these things ourselves. And while that may sound like a problem, it's not more than of a problem that you would have if your entire code base was in C. When you're passing a pointer to a function in C, you still need to have an understanding of the code that is so good that you can guarantee you're not going to have that you're not forgetting to take a log, or that the code you're calling into is not forgetting to take a log or something like that. So at this boundary, we need to have a really good understanding of the code that we're calling into so that we can assert these safety invariants. And so to do that, we're using the unsafe keyword in Rust to like opt out of the safe subset. And when we use this unsafe keyword, the compiler, it still functions the way that it does when we're in safe Rust, but it allows us to do some additional things. And those are dereferencing raw pointers, calling unsafe functions, including the C functions we have in the kernel that we need to call to interrupt. We can access, it's a funny one, the middle one, but accessing a static variable immutably is not safe in Rust, so you can't do that. If you have a global, you need synchronization to do that. Unions also, if you access a union, you have potential type confusion. If you're not, so it's basically just disallowed in Rust. You can't do it without the unsafe keyword. So how are we going to go about and deploy Rust in the Linux kernel? Well, we want to support, because most of the issues we have in the kernel is in the driver code, we want to support development of device drivers completely in safe Rust without any unsafe keywords in there, so that we're sure that the code we get in the drivers is completely safe without any memory safety bugs in them. So we are writing some thin abstractions on top of the C APIs we have, and we are constraining the unsafe portions to tiny areas. And then we are focusing our review bandwidth into those areas where we have potential problems. And we believe if we do it like that, if we can get those pieces right, then the rest of the system is sort of automatically safe. So I'm just going to talk a little bit about the Rust for Linux community. So the Rust infrastructure was merged into the kernel in 6.1, and the Rust for Linux group has been part of the kernel community since then. We have a Zulip chat platform where if you're interested in this project, you can go there and ask questions. People are very helpful. We also have a mailing list where you can send patches, or you can follow what's going on in the community and who's building what. And if you want to submit patches, the way the contribution is set up right now, or what do you call it, the way the process is set up right now is, if you have anything like only Rust related, you submit it to the Rust subsystem. But if you're building abstractions for memory management or block device drivers or something, that goes through the respective subsystems and has to be reviewed in there. We also have a website that's a really good resource, and we have a GitHub repository that we used GitHub prior to the merge. And now we didn't merge all of the stuff we wrote into the kernel, so we use it as sort of a backlog. And we're also talking about having, since we have a lot of individual projects ongoing, we are considering having all of them hosted in the GitHub, like until they are merged. So this is, since we were merged in 6.1, I believe it was during the Plumbers conference last year in Dublin. The first stuff we got in, you couldn't actually do anything with it other than print "Hello World" from a Rust program, and then that was about it. We then later got some error handling and some vtable stuff, which is we're using for anytime you'll have a structure that's full of pointers. We have a macro to handle that in Rust. In 6.3, we got those of you that are familiar with Rust know the arc, which is a reference-counted smart pointer, so sort of like the C++ shared pointer. And this particular version is backed by the refcount kernel data structure. We have like a scope guard is like it will run a function for you when it goes out of scope, so you can use that to deallocate resources automatically. We later got the pinned init crate, which is sort of important because in Rust you have move semantics by default, and some data structures in the kernel are actually not safe to use before they are initialized. And that, for instance, applies to the mutex, which has a lists node inside. And when you just, the initialized state of a list node is so the list node has 2 pointers back and forth, backwards and forwards, and they should point to the node itself when it's just, when it's the empty list. When you insert it, you sort of link these pointers in. And when you just allocate memory, you have, these pointers will be null. So allocating this structure in Rust is actually unsafe unless you call the initializer function after. And now we have some macros that can make that happen, because you can't do that in Rust by default. And then we have some upgrades to the tooling, and the next thing that will go in is probably abstractions for the work queue, so we can use that. This is a non-exhaustive list of projects that's currently being worked on. I think, so we don't have any drivers merged into the kernel yet. And we're sort of not sure which is going to be the first, but if I had to guess, it would probably be the Android binder driver. So Google is rewriting, binder is an IPC mechanism that's used in Android, and it's also available in the Linux kernel. And there has been a number of security vulnerabilities in that driver, so Google is rewriting that to Rust to prevent these issues. And that will probably be some of the first stuff to go in, I would guess. Yeah?
Before you move on, so you're writing this in a different language. These are modules that currently exist in the kernel. How are you working with the current maintainers, or are you writing something that's separate from it? Or?
So it really depends on the on what project we're talking about here. The
Block NQ and NVMe I'm particularly interested in.
so the no. So I'm working with the block layer community to figure out a way for this. So the goal, what we're interested in at Samsung, is to provide infrastructure to build block layer device drivers in the future for new hardware. We don't want to replace the NVMe driver or necessarily the null block driver. But in order to build these abstractions, we need reference implementations, and that is causing some friction in the community because there are. So this is actually a very good question. The rule in the Linux kernel is.
The question, I couldn't hear him.
The question was whether I'm working with the community to upstream some of these projects.
Is it a replacement commit or a side commit?
So the null block, the NVMe driver is not targeting upstream. I want it to be a reference implementation. The null block driver is targeting upstreaming, so replacing null block. And there has not been discussion in detail about whether or not this is going to happen. Okay, but it's sort of, we have a sort of a chicken egg situation here. we want to be able to build these abstractions, but to do that, we need a driver to drive the development. And as I was saying, the rule in the kernel is you can't have duplicate code. Okay, so if there's already an NVMe driver, don't write another one. It's not going to go in because we already have one, which makes sense. Yeah. But because we need these reference implementation for two things. First of all, to drive the development of the abstractions, and in my opinion, it's better to use something that we already have a C reference implementation for, so we know that we're not regressing in performance. And it's also, as a resource for existing kernel developers, it's nice to have something they're familiar with when they're getting into Rust, right? And therefore, there has been some discussion about an exemption for Rust for this, but it's ultimately up to the maintainer of the subsystem. Yeah. All right, so there's lots of interesting stuff going on. Some of it is completely new hardware. For instance, the Apple M1, M2 GPU driver. There is no C driver for that. And I believe there's also not a TLS handshake in the kernel that was deemed too dangerous and not put in. Someone wrote it, but it's not in. And now the developer thinks that because we have Rust, we can guarantee a lot of safety properties, and then maybe we can have it in the kernel. So then some of it is wrappers around APIs, and some of it is end modules. PuzzleFS is a container file system developed by Cisco that they use on their switches for running containers. All right, so the multi-queue block device drivers. Let's get into that. So this is a figure of the storage stack in Linux from a paper by Jens Axbo and Matthias Bjørling. I think it's a very nice figure because it shows what's going on very nicely. Up top, you have your user space processes that are generating I/O in one way or another and submitting it to the kernel via one of several interfaces. The I/Os hit after going through the kernel boundary. At some point, they will hit the block layer. And in the multi-queue stack, we have a number of per core queues where we will enqueue the I/Os. And in this layer, we can do stuff like quality of service and reordering and merging and stuff. And then when we're done with that, we submit the I/Os to some hardware queues that are, the number of those are limited by the hardware. So for instance, in the case of NVMe, you might have less hardware queues for your device than you have a number of cores. And then we have some kind of funneling into these hardware dispatch queues. But the default is to spin up a queue for each core if you have enough queues, because then you have no sharing of the data structures through the stack. And what we're going to talk about next is the little red box. That's how we interface the device driver to this hardware queue layer. And you're not supposed to be able to read this, but it's just to show, like, we have some Rust and we have some C. And what we have to the right is a struct full of function pointers. And what we have to the left is a Rust trait. A Rust trait is sort of like an interface. You can implement it for a struct, and then that struct can serve as a type. It will have that type bound. So if we implement this trait for a struct, we can use that trait as a block MQ device driver. And I'll just zoom that in a little bit for you. So here I cut out the queue request function. That is what the kernel will call into to queue a request with the block device driver. And at the bottom we have the C type def of the function. And up the top, you have the Rust version. And so some things to note here is we have two associated types. So, and one of them is the Q data, the other one is the hardware data. The Q data is data associated with your gen disk, so that would be like your NVMe namespace in the case of NVMe, and the hardware data is the per hardware queue data structure. And these are typed, so you're not going to access these like void pointers and then cast them because you happen to magically know what they're going to be. If you don't do this right, the compiler won't let you build the program. And so we pass this hardware data, the queue data, and the request to this function and execute it. So as I said, this is a trait, so we have to implement it for our struct in order to use it as a device. And for the null block that I've written, it looks like this. This is all of the code. So now this particular implementation of the null block has fewer features than the C corresponding C code. So that's also why it's tiny. But it's also very usually Rust code will condense to something less than C. And so just to go through here, you can see in this case the hardware data is not the per core hardware data is nothing. In Rust we have it's called the unit type. It means like null basically, or nil or whatever. And we have the per queue data, which is the per block device data. That's a tree, which is it's a mapping structure. It's actually a radix tree. It's a wrapper around the C radix tree. So you can put in a number and get out an object. It's like a map structure. And we have wrapped that in a spin lock. And we have the request, of course. And then you can see what we do here is we start the request. We check whether or not we are implementing a memory. So I should quickly elaborate that the null block driver is a piece of testing infrastructure that you can send IOs to, and it will just say, okay, the IO is completed, and throw away the result. Or you can enable this memory backing feature, and then it will actually put the IO to memory instead of to disk and like simulate a disk drive or a block device. So we're asking whether or not we are memory backed. If not, we're just ending the request okay. If we are memory backed, we're going to grab our tree by taking the lock. And one thing to note here is if we are not taking this lock, then we can't access the tree. We can never forget to lock. And if you've ever patched some code that relies heavily on locking and is heavily multi-threaded, you might appreciate that it's difficult to get it right, especially if you didn't write the code yourself. It's not trivial to make sure that you are locking the data structures correctly. And if you're not doing it correctly, you're going to have a race condition. But here we can't forget to lock because the compiler won't let us. The object we are accessing is encapsulated in the lock. We also cannot forget to unlock, because once this mute tree we have as the first line in the if goes out of scope, the lock is dropped. Okay? The rest of the code is just iterating through all the BIOS in the request. It's like the request has a linked list of BIOS, and each BIO has a scatter list of pages, and then for each of these pages we do the transfer. And just to show how this prototype would look for the NVMe device, I put it up here. The implementation is a little big, so I didn't want to put that. But here you see like our queue data is the NVMe namespace, and the hardware data is an NVMe queue. So we can specialize like that. So where is all of this unsafe code, where we interrupt with the C code? So the kernel is actually not calling this Rust function directly. It's calling into a a function marked extern C that has C linkage and can be, how do you say it? It will have the same calling convention as a C function. So the kernel code can call this directly without any problems. So what we do here is the first line is we're unpacking the request of the block MQQ data, and then we are converting this hardware context device driver specific data into the target type. And that's unsafe because if we're doing it wrong, well, it's unsafe for multiple reasons. One of them is we're dereferencing the HCTX pointer. And if that is null, we're going to have a null pointer dereference, and we're going to segfault, basically. And that's what I was talking about before. There's no way for the compiler to make sure that this pointer is not null. So we're going to have to rely on the people who wrote the kernel. They said, this is never going to be null when we call this function. Trust that. So we're going to have to trust that. Like at some point, we're going to have to make this cut, and this is where we do it. The rest of the unsafe blocks is more of the same, because we don't know whether these pointers are as they should be. We have to use the unsafe keyword, dereference them. And the call to the queue request Rust function is in, let's see if I can point here, right here. So because this function is generic over this type T, which is the type we're implementing the trait, the operations trait I showed you before, we use T because we don't know the concrete type. It could be like a NVMe driver or a null block driver. And then we're making the call right here. So how when we have all of this unsafe code, how are we going to make sure that it's right? In the Rust for Linux project, we have a protocol for commenting and describing the unsafe call sites and any function that's marked unsafe. So to call it, you remember I said to call an unsafe function, you need to use the unsafe keyword. And if we have a function that potentially has that is unsound if you use it wrong, then we mark it unsafe, and we put some safety requirements on that function. And that's what we've done here. You can see like yada yada yada. The caller must ensure that these are valid and initialized, and it goes on and on about the requirements for calling this function. So if you don't uphold these requirements, then you will have undefined behavior, basically. And similarly, on the call side, whenever we are calling into something that is unsafe, or whenever we are doing an unsafe operation, we are specifying what did we do to make sure that this is actually not going to invoke undefined behavior. And this is just in regular human readable language, so it's sort of anyone can reason about it. We discussed actually having it as more like a proof language, but in the end we think it makes more sense. It does not make sense to impose yet another language on kernel maintainers. Rust is enough as a first step. Yeah. You can find this code online if you are so inclined. Both the NVMe driver and the null block driver are based on top of what's going to become 6.6 when that is released. So the last bit of the slide deck is some performance numbers that I've run some benchmarks and obtained some numbers. So this is the NVMe driver. I don't think it says so, but it is. And this is the latest code rebased on Rust Next. It's running on an Intel workstation with an Optane drive that does around 1.2 million IOPS. And you can see here let's see, you have On the left graph, I have a number of different block sizes, and then I'm sweeping over the queue depth. And on the right side, it's the same data, but it's just the 512 block size. And the C driver is slightly faster until we hit the limit of the drive. So probably it's still faster, the C driver. If I had happened to obtain a faster drive, I would probably see that the C driver is still faster. There can be many reasons for this, but I believe probably lack of inlining across the languages is the primary thing right here. So I'm working on that, and as soon as I get it to work properly, I will post some new results. I can tell you that for my workstation here, when you're enabling LTO, the kernel does not boot. So I'm sort of looking into that. All right.
I presume that that's an incorrect y-axis. Okay.
The y-axis, it's
IOs per second, and you've got a point gauge right next to it.
yeah, but it's 1 to the times 10 to the power of 6. So it's millions. Yeah.
What was the question?
The question was whether the y-axis was correctly labeled. The y-axis is labeled in millions of IOPS per second.
Do you have CPU utilization results for this graph?
I do not have for this one, but I can tell you that for this one it's 100%. Right? So yeah, for one core, like 100%. For 1 million, it's not going to be 100%.
What was the question?
The question was, do I have CPU utilization numbers for these benchmarks? Thanks for reminding me. So this benchmark is run on this is on an older code base with another drive. It's a P5800 drive that does I believe it caps out at 5 million IOPS. And here we go to in this scenario we add more drives and cores. So like one drive, one core, two drives, two cores, three drives, three cores, and we see that we scale sort of similarly to the C driver. And for vertical scaling, so we keep only one core, and then we add more drives to that one core. That one core has to pull more the queues of more drives, and therefore we can't get the same kind of performance. And again, we see the C driver performing slightly better than the Rust driver, except when the drive is bottlenecked. When the drive becomes a bottleneck, it doesn't matter. So the last bit of the deck is performance numbers for the null block driver, and I have just a little the statistics I talked to you about in the beginning. I have them broken down here, and I have a little bit of information about the null block driver. It's no more than 147 lines of code. 100% of it is completely safe, so we can assert that there's no memory safety vulnerabilities in that. The null block driver has some unsafe code. Sorry, not the null block driver. The NVMe driver has some unsafe code in it. It's a bigger project, and it's sort of a work in progress. I believe that eventually we can remove all of the unsafe code from that. So this is a FIO random write workload with using IO-Uring with a queue depth of, what does it? I can't read what it says. It's like 16 or 32 or something. And here we have on the x-axis, we have number of jobs. Each job is pinned to a CPU core. I happen to have 6 CPU cores in my workstation, and therefore it goes to 6. And there is an interesting pattern going on here. Basically, for smaller IOs, the Rust driver performs better up to 12%. But as we grow the size of the IOs, it begins to perform worse and worse. And you can see on average it actually performs a little better than the C driver. So I believe one reason for this happening could be that as we are, when we're going to the larger IOs, we're spending more time in the I showed you before, we have like a double loop. We are iterating the BIOS, and then for each BIO, we're iterating the BVEC list, the scatter list. So we're spending like more time in that loop. And if we're not inlining correctly in there, then we're going to have worse performance than the C, probably, right? But then again, the null block driver here is it has way fewer features than the C one. So on the path into the place where you actually do some work, you have fewer instructions, and I think that's probably why we're seeing the performance boost for the smaller block sizes. So I think that once we get to feature parity, we're going to see that performance benefit probably even out, and it's going to be roughly the same, since like they're going to have more or less the same instructions in there. So I see no reason why it should not be more or less the same. Just for completeness, I also put a random read, and like this is a single run. So there's a little bit of noise in the measurements, but we still see the same overall pattern. Yeah. Any questions? Yeah.
Yeah, I was curious if you could clarify a little bit what NVMe driver is. This mainly like NVMe core module or the PCI transport? Or?
So the question was if I could clarify how many features we have in the NVMe driver.
Or just which part of it, right? NVMe consists of like core module and then all the different transports and drivers.
Okay, which parts of the C NVMe modules are we covering in the Rust? So this is only for PCI. There's no fabrics, no no CNS, it's vanilla NVMe. So you can plug it into you can actually run it on your laptop, but you're not going to run it in your data center, probably. Yeah. Yeah.
Yeah. I'm new to Rust, so I know what the disadvantages and limitations of Rust versus C.
So the question is, if you're new to Rust, what is the disadvantages and limitations of Rust compared to C? And so I guess it's a sort of a weighted question, because I would say there is none. It's much better. You should use it. It's awesome. But it is also not the easiest language to pick up, because you have this limitation that you can have at most one writable reference to a piece of data, or you can have many readable references, and that takes some time to get into the like what patterns match well with that programming paradigm, and so there's like some getting used to that. But once you have that, I would say it's pretty much a win.
My point that there is one aspect that we covered today, which is safety, memory safety, right? So I wonder if there is other aspects that we can consider when comparing C with Rust or any language with other languages, right?
Well, so I think it's much so the tooling around the Rust language is really excellent, and because the type system is so strong, you get a lot of help from the compiler when you're writing the code. So it feels like writing in a very I'm not sure how to put it. There's like the developer experience is better in my opinion, but it's difficult to argue about, because some people who's been writing C for 30 years, they very much prefer to write in C, right? But I think you can think of it as the jump from assembly to C, sort of. It's a more modern language with more features. Right? I hope that answers your question. Yeah?
Sometimes people value security by the number of lines of code that you ended up reducing. Did your implementation actually reduce the lines of code compared to C? I don't know if that's the right metric to ask as well.
So the question was a statement that some people count the reduction of number of lines of code as as better security, because I guess because there is fewer lines that you can have problems in, and whether my implementation reduced the number of lines of code. So it's I can say yes, my implementation is smaller. My null block implementation is smaller, but it's also not. It also does not have the same amount of features as the C version does. I assume and expect that the full implementation will also be very much fewer lines than the C version, and that is because we have all of these. We don't need to be explicit about cleanup code. We don't need to be explicit about unlocking our locks. Unless we want it to happen at a very specific time, we can do it manually. But in general, you'll have less code because you have much less cleanup code, and you have more powerful abstractions for the stuff you're interfacing with. And that's also what I see in. I'm just trying to recall someone writing. Yes, so Alice, who's doing the Google's binder driver, had some slides at the Rust for Linux workshop in the weekend, and she was reducing the number of lines of code by, I believe it was 1/3, and she's feature complete with the C binder version. Yeah. Yeah, Joel?
About calling, I know that answer, but I want to see if there's some Rust something. How about calling assembler from Rust? Is that something that, is there a special, like, this is the way you call assembler from Rust, or you just like, okay, that's insecure, and then you just don't do it?
So the question was, can we call assembler from Rust, and whether or not we should do it if we can. And it's no different than calling C. You can call any symbol you want, but you need the same kind of verification when you do it, right? It amounts I think it can be compared a little bit to having inline assembler in C. Like you need to, I think you specify to the compiler like these and these registers. It's not the same, but it's sort of like you need to make sure that you do it right, or it will blow up. Yeah.
So what's next and what's the end goal?
Well, so my goal and our goal at Samsung is to make it possible to write block layer device drivers in Rust. That's what we are focusing on. We think that has a place, and that is valuable to have that option. To that end, we are having the NVMe driver to drive our development of the abstractions, and we are pushing the null block driver to replace the upstream null block driver. Whether or not that will happen, we will have to see. As I said, right now it's like a proof of concept. It's not feature complete at all, but I'm working on getting it closer to that. Mm-hmm.
I think a lot of the hard work here sounds like the trait coverage and the API coverage. Can you comment about how much of that is done and how much remains? Or?
So the question is, it sounds like the hard work here is building the abstractions for the APIs we want to interact with, and how much of that is done. And the kernel is big, so it's not a lot of it is done. We have done a tiny fraction, and we have a lot of abstractions that are not merged upstream, but that are ready to be merged when the subsystem maintainers has reviewed them. But there is another rule in the kernel: is we're not merging dead code, so we need to have a user before we can merge them. And so we have this chicken-egg problem. We need users to be able to merge our stuff, but we need abstractions in order to get users. So, yeah. Does that answer?
Yes.
Yeah, great. Any more questions? All right, thank you.